Nalewajko. He now works in CAMK. He graduated from Warsaw University in astronomy, and then he did his PhD in CAMK. And after that, he went for a couple of fellowships, first in University of Colorado in 2013, and then he received NASA Einstein Fellowship to spend it in Stanford University. And after coming back, he's now at the position in Copernicus Center. He will tell us today about magnetic reconnections in blazar jets.
Yes, and not only magnetic. Thank you for this introduction, and thank you for allowing me to speak here. I have returned to Poland last year, and I am continuing projects that I started during my postdoc years at the University of Colorado. So
in Boulder?
In Boulder, yes. So Dmitry Uzienski is like my plasma physics expert. He is in at the Center for Integrated Plasma Physics, and Mitch Bigelman is an astrophysicist. And when they met together, they actually started this investigation. Greg Werner is a postdoc. Benoit Ceruti was a postdoc at Colorado, and he is now in France. And then at Stanford, there's a group of postdocs and students that were collected by Roger Blanford, who is independently interested in this topic. So I'm talking about relativistic magnetic reconnection, and the word relativistic is motivated almost exclusively by astrophysics. There are other research areas, both experimental and in space physics, solar physics, but relativistic reconnection is refers almost exclusively to astrophysics. So, however, I should start from. I should begin from showing you something that is very familiar, and also something that we can almost touch. The solar flares as observed by modern space telescopes. They are truly spectacular events. However, what we know about them today is roughly has already been first understood in the 40s and 50s. And the first paper that proposed explanation for the solar flares from particles being accelerated by induced electric fields, especially in the magnetic neutral points. This was propositioned by Giovanelli, and in the 50s, a standard fixture was developed by Parker. It involves two sunspots having large magnetic fluxes, and they are, however, they meet in a way that magnetic field lines are locally anti-parallel, and then those field lines reconnect. They change their topology, they merge, and in the process they release magnetic energy. And so,
what is magnetic energy?
Magnetic field.
Magnetic energy. These were over
One half, but then can you avoid generating also E?
You generate E, and E is like a so first by motion of the magnetic field lines, you induce electric fields.
Yeah.
Electric fields then accelerate particles. So effectively, the energy flows from magnetic fields to the particles.
Okay.
Eventually, I will mention later, particles may radiate this energy. So we are looking into reconnection as a process for accelerating particles and producing high energy radiation. Okay, so then there are well-known examples of reconnection working at the interface between the Earth's magnetosphere and the solar wind. And there are two such regions. One is on the day side magnetosphere, which interacts with the solar wind, and a second is at the magnetotail. And they are both accessible to space probes. The most recent that was released is the MMS that will has a goal to probe the three-dimensional geometry of reconnection in space in the Earth magnetosphere. Then also other planets, some of them have strong magnetospheres, and for example Saturn has a very extended magnetosphere. This is just a cartoon picture. There are some recent results coming from Cassini mission that probed the magnetic fields in the magnetotail of Saturn, and they found evidence for sustained reconnection. In reconnection, we are still quite unsure whether it can operate as a steady-state process or whether it is highly intermittent. Okay, and now these examples that
Excuse
you
me,
can...
but
Yes.
what was precisely found by this Cassini mission? Which is interpreted as a proof of reconnection?
So don't remember exactly, but it is it must be there must be electric fields that are sustained by reconnection. I don't remember this exactly.
And in the case of the sun,
In the case
these
of
are those
Yes.
kind
in the
of...
case of the sun, we have both solar flares, which produce radiation, as hard X-ray radiation, and gamma rays. In the quiet sun, there are also many tiny substructures, chromospheric jets.
But on this movie which you
Yes.
showed, very impressive.
Yes. So
So we are now, these are those kind of rays which are interpreted as charged particles are accelerated
Right.
in the electric field along the magnetic field
Yes.
lines
yes.
and radiating, right? And
Yes.
this is
And the thing is how to of course accelerate those particles. Now this shows this only shows this is extreme UV image, so these are very hot regions, but they are not. In addition to that, there's plenty of X-ray emission that is not as well resolved. So today we can only approximately associate X-rays with those structures, but also well, gamma rays are there is another possibility, but basically it is this radiation illuminates individual field lines, and so it is possible to study the actual dynamics and also measure how the magnetic flux changes in those active regions.
roughly.
This is of course accelerated a lot in real time.
Yes,
that looks-
yes. Of course, this return just falls like it's Earth Sun's rotation is
Yeah, that's
are
right.
like 25 days, so this is yes. That's,
25 days in 1 minute.
so for those plasma that are accessible in new space and also in the solar corona, they are characterized by relatively weak magnetic fields, which then means that their magnetizations are much below unity, and magnetizations scale the Alban velocity or other characteristic velocities, and so the velocities that are induced, the bulk motions that are induced by reconnection in these plasmas are non-relativistic. However, it turns out that in astrophysical environments, especially related with black holes and neutron stars, sigmas of order unity and larger, maybe even much larger, are possible. So I will mention two astrophysical motivations for this. One is the pulsar wind nebula. The Crab is the first pulsar discovered, and the nebula is this large structure observed here by Hubble telescope. So it has these filaments, but also a diffuse non-thermal emission, and it has a spectacular spectral distribution. It is observed all the way from the radio. This is optical UV, these are X-rays, some soft gammas, then gamma rays from Fermi, 100 MeV, 1 GeV, then gamma rays from Cherenkov telescopes, and this is well described by this model dominated by the synchrotron emission and synchrotron self-compton for the gamma rays. And this spectrum is so important in astrophysics that it was considered like a standard for high energy astrophysics. For example, Fermi was and other gamma ray telescopes are being calibrated with respect to the Crab nebula. However, it is thought now that we have a pulsar with some misaligned magnetic, like the field can be approximated as a dipolar, although we don't actually know. It is just a model that the field is dipolar. There can be more complicated structures. The field within the so-called light cylinder can co-rotate with the pulsar. At large radius, the magnetic lines have to open, and then there is the complex structure of the wind, which has to go from highly magnetized state to a weakly magnetized state over this distance scale. Then it approaches a shock front, and because this shock is strong, it is then the question about the mechanism that could convert highly magnetized plasma. The particles are probably the only plausible way to introduce particles here is by pair creation, but this is highly uncertain how many and how efficiently those pairs are being created. But eventually we expect that this flow converts to a
I don't understand the shock front. This would mean that there was some event that created this shock wave.
It's like
the shock wave front is moving, right?
Well, so the pulsar is being slowed down by magnetic field. So it basically emits this pointing flux, or say the magnetic energy,
Yes.
and it interacts with,
That's
it collides
true,
with
but
the
shock front
environment.
suggests that there was some event that created this wave that has a front.
Yeah, but
So where
I
is
think-
this shock front?
But if people think about this as a stationary shock, Where-
Stationary.
yeah, so it will,
So
so
it's not moving.
it's not necessarily moving. It may be, at least we probably cannot even know that, but there is a shock solution is possible with this is high relativistic flow, and then it will be slowed down, so there will be still outflow. This is not like this. You still have outflow, and actually the nebula itself is even much larger than.
So it's not really a front.
Yeah,
It's not really a shock.
It may not be well. What we just know from observations, there are some. We barely resolve the shock, and so there are structures that are being associated with it, and I should say that this shock may have geometry like figure 8, and we may actually observe signatures of this shock at these more polar angles. But the shock is it was proposed in the 70s to explain dissipation and the radiative efficiency of the nebula. So it's as in many cases in astrophysics, this is not well. This is a standard element of the model, but it's not proven definitely, I would say. Okay, now the Crab nebula, which is emitting in the gamma rays. These are gamma rays measured by Fermi. These are photons above 100 MeV, and typically GeV photons. The Crab nebula actually shows some time variability, and during these flares there is a component in the gamma rays. So this is again 100 MeV and 1 GeV photons. There is a component that appears just in the middle between this large synchrotron component and this synchrotron self-component. And these flares have introduced a number of problems. They have a variability time scale of a few hours, and from this we infer that this is still synchrotron emission. However, synchrotron emission and as it is being exemplified here, it is cut off at around 100 MeV. This is now this cutoff appears to be quite fundamental. At least if your electrons are being accelerated by electric fields that are limited by the magnetic field. So in for example, magnetohydrodynamics, electric fields are induced by motions of magnetic field, and so they are cut in the CGS units. E cannot be greater than B, and putting it another way, if an electron is gyrating in the magnetic field, and at every gyration it may lose most of its energy, even at like a quarter of the full gyration. This also corresponds to a limit on the synchrotron photons, and this limit is 100 MeVs unless you can have electric fields that are much stronger. That means non-MHD. And so this result motivated new reconnection studies of reconnection in relativistic limit, because this was one of the most plausible solutions for explaining these flares in terms of synchrotron radiation. Okay, now the second motivation for studying this comes from relativistic jets. So these are radio images of radio galaxies. These are galaxies that have a nucleus, AGN, active galaxy nucleus. It forms a pair of jets, and here those jets appear roughly in the plane of the sky. The jets power these large diffuse radio lobes. In another example, this is radio galaxy M87. It has the closest and the most resolved jet that we can access. So to indicate the scale, this is in size of hundreds of kiloparsecs, and here we are probing fractions of a parsec. We can resolve it. This galaxy has a massive black hole that we can resolve down to 10 or 20 Schwarzschild radii, and this is one of the targets for the Event Horizon telescopes. However, now the jets are called relativistic because they one of the reasons is that they show superluminal motions, and this cartoon shows that over a range of almost 7 years, there is this core in the radio image that is aligned, and now a feature that is propagated apparently over more than about 30 light years. What is happening is that this is a projection effect. Superluminal motion is just apparent motion, but it indicates that there is a truly relativistic flow. That it means bulk Lorentz factor much higher than unity. And now the best way to accelerate, the best theory for accelerating jets to relativistic motions involves conversion of magnetic energy to the kinetic energy. So there are some models that have studied acceleration by means of simulation, but there are also some semi-analytical results. And basically, what is happening is that magnetization of the fluid, called sigma, is being converted into the Lorentz factor of the flow. So in order to have relativistic motions, we need to have highly magnetized plasma at the base of the jet. But also these jets, if they are now aligned with the observer, they show enhanced variability and also variability on very short timescales. Variability on timescales of a few minutes is actually shorter than the light crossing timescale across the black holes, the supermassive black holes at these galaxies. So even so, these are these observations, and they restarted around 2007. They motivated a previous wave of reconnection studies, and in particular, there is this model called mini-jets model, where we have a broad jet that is already relativistic, but consider that it may have reconnection sites, and reconnection would produce locally flows with additional Lorentz factor, and especially if this additional Lorentz factor is perpendicular to the jet axis in the comoving frame, then the Lorentz factors multiply, and the short variability timescale requires these large Lorentz factors because otherwise the gamma rays would be absorbed by soft radiation. But in this case, we can also explain emitting regions that are much smaller in size than the cross section of the jet, much smaller than the black hole crossing radius. Okay, so now let me just show the basics of magnetic reconnection. This is a cartoon showing magnetic field lines that are anti-parallel. They don't have to be completely anti-parallel, but they should have at least an anti-parallel component. Those field lines can extend to very large sizes, but now one can imagine a steady-state process in which those field lines are being brought into the region with some characteristic velocity called reconnection rate, and there is then magnetic diffusion region where those electric fields locally dominate over the magnetic fields, and actually here is one of the prime sites for particle acceleration. But magnetic diffusion means that the lines that are frozen to the plasma can now reconnect, and they will then be pushed away from this region, and they basically can approach, the plasma can then be accelerated to velocities of the order of Alven. And now in relativistic reconnection, as I mentioned, this Alven velocity, it's actually Alven velocity with respect to this upstream plasma. It can approach the speed of light, so we can have in principle bulk motions away from the reconnection region, in addition to also acceleration particles to very high energies. But now, because this problem has a relatively usually has a relatively large aspect ratio, there is like a global scale of the problem called L, and then the thickness of this region is of the order of either the skin depth or of the characteristic gyro radius, and so this is usually orders of magnitude smaller. So this is very this is in principle very thin, should be very thin structure. If it's thin, then by mass conservation, if we have even relativistic flows, outflows from the region, the reconnection rate will be quite limited by this aspect ratio, and the process will be not total. This was one of the main reasons why there was a suspicion that this may not be very efficient. This slow reconnection rates, of course, also mean weaker electric fields.
You mentioned that this happens in the vicinity of a black hole. So what is the mechanism that produces these anti-parallel magnetic fields?
Right, so inversion of the global inversion of field lines is actually the most difficult part of this problem, because we can consider what happens once we have those inverted field lines. Now how we can get them. So there are scenarios involving, for example, in black hole jets, one can imagine that. So black hole jets, they appear to be the field lines are probably supplied from the accretion disk. If the accretion disk has domains of opposite field lines, and if they are brought to the jet, then there will be eventually those domains may appear, may be present on both sides, and they will locally reconnect, even if it takes some distance for them to meet and be pushed against each other, because the jet would push those fresh flows against those previous flows. But also the jet itself can be maybe unstable, because initially it is dominated by colloidal fields, and then due to expansion the fields become mostly toroidal, and toroidal magnetic fields are prone to instabilities.
What creates this asymmetry? We have
Yes.
accretion on the black hole.
Yes.
Why does
Well,
this
it may be that so there either may be a dynamo operating in an accretion disk, which is
so is this a curve solution that has
yeah,
the black
this,
hole rotating?
right. So we can consider a curve solution, and spinning black hole has produces more powerful jets. So the background is can be a curved black hole, but now the field lines. So we know that the relativistic flows they really have those field lines connected to the black hole, but now
But magnetic fields must be closed. There are no magnetic.
right. So it will
It
once it opens up, and there must be some.
So black hole
It is in the
becomes a
current picture.
Is it true that black hole is like a magnet?
No, not really, because
Itself,
those
it's kind of
fields are opposite.
no. It may it's it well effectively yes. It will black hole will have a net magnetic flux, but the magnetic flux should cannot. We don't know of a process to create the flux at the black hole, but once something is accreted on the black hole, it will carry the magnetic flux with it, and while the particles will go into the black hole, the flux will always stick out unless well.
Is there a model that really explains it?
Well, there is a lot of debates to this day, and because this is a problem which has
It's a relatively simple conceptually problem.
Yes.
There is a center of attraction and there is a matter falling.
but right, but there is not a simple model of accretion. Like say, what is the problem is really comes down to what is filling the black hole. There may be far away on these parsec scales. There may be independent clouds of gas which carry some amount of magnetic flux, and they will eventually form the accretion disk, and they inherit this flux. And if the flux, I would say one of the paradigms for creating jets. We know that only 10% of black holes create jets, and it seems that the first thing that must happen is that magnetic flux needs to be collected at the black hole in order for the jet to appear. And this may take many years of accretion, or even merger. It may come from merging a galaxy with some other galaxy, which would introduce cold gas with magnetic field lines. So alternatively, there are theories that the flux, there is a dynamo in the disk, and then due to buoyancy, those field lines may actually have these global structures. But it is a difficult problem. I should mention now, we can imagine a scenario, easily a scenario where there are no inversions of magnetic field lines. Like the jet is just having, the jet has, as I mentioned, colloidal and toroidal field lines. But they may have, you may even consider that there is no inversion that is inherited from the accretion. But because of the expansion, and if there is any small toroidal field component, it will eventually become dominant at some distance scale, and toroidal fields they kink. The toroidal fields they toroidal fields pink, they make these current-driven instabilities. The fastest growing mode is M equal 1, and if it goes non-linear, then then there will be some local inversions of the field, and this may dissipate part of this energy of the jet.
But the
So
matter that is falling on the black hole is neutral, isn't it?
It is,
Cannot have charge.
but it's very hot. It's fully ionized.
But it's
For
a plasma, so
yes.
it's
Yes.
globally it's neutral.
It has it's globally neutral, but it's completely ionized for AGNs, and
Still, the electrons and ions are mixed.
yes,
The neutral
but
plasma.
Yeah. What about the sun?
sorry.
Yeah, but what about the sun? The magnetic fields have random anti-parallel orientation in the sun, right? We saw this reconnection mechanism just with a naked eye or a telescope, right?
From the sun, we know that the motions of the photosphere, they can bring the sunspots together, and they don't actually like to be together. They would repel, but they are forced into this interaction by motions of the plasma in the sun. So and by analogy, we think that that accretion disks can transport field lines, although it appears that actually there must be geometrically thick accretion disks for this to be efficient. The geometrically thin accretion disk would feature, if the field would like to, there are mechanisms for the fields if they are only being driven by thin accretion disk to escape outwards. So this is quite complicated. I would say that the scenario I would advertise is that there is a episode of geometrically thick accretion that is bringing the field onto the black hole, and once there is a sufficient magnetic flux, a jet will be created, yes, and then there is the next question is how it can dissipate this energy. I should mention also that for blazars, those jets that are pointing at us, neither they are relativistic, they are very luminous. They have even correcting for Doppler beaming, we have a problem of radiative efficiency. That what we observe, we convert into the power that is needed in the jet to support this radiation, and we approach often a problem that if radiative efficiency was low, the jet powers that would be inferred are unreasonable. That they would exceed, for example, the Eddington power. Yes. Okay. Let me continue to show because in fact now I will focus on the workings of reconnection, and basically from analytical studies there are these two basic models. Why they describe the Sweet-Parker reconnection, which has this long slab and very thin. It's quite inefficient. So there was this. What is also featured in this model, there are these structures that are diverging, and there was an idea that if resistivity is localized, it would support this Sweet-Parker type reconnection, collisional reconnection here, and then would be slow magnetosonic waves that would also process the fuel bank, but this mechanism was not realized, but I would say these models dominated for 40 years in the literature, and there was probably not a very rapid progress in reconnection studies. By realization that these systems must be very large, we now know that they cannot be they cannot be so steady state as in this picture, and that there are instabilities of the current layers that produce a complicated chain of plasmoids. So I mean, these X points, like we have the magnetic, this is just magnetic topology, a point where you actually diffuse the fuel lines. This is an X point, this is a single X point, and now we have consider models with multiple X points that they arise from the instability of the.
When you say a model, that means that there is a set of equations of magnetohydrodynamics,
yes.
And these equations differ from this model to this model.
Right, they are slightly, yes, so there is like there are equations concerning the conservation laws for inflows and outflows, and some assumptions about the thermodynamics in the layer. And then
are you going to show some of these equations?
No, I didn't prepare it this way.
Well, because a model means that there is a well-defined mathematical.
Yes. However,
after all, this is magnetohydrodynamics at the end.
Yes. Yes, but the problem is that for large systems the problem becomes highly nonlinear.
Of course, it's.
And that's what we've been doing. Yes, so I would probably need to make a more historical presentation on these models. But they are pretty simple. You just consider mass energy conservation for the inflow and outflow, and
but mass energy conservation is not enough to set up a model.
Yes, of course. But this is one of the key elements. Yeah, it's a necessary element.
But in your research, you're dealing with some.
What we are doing simulations, because we realize that reconnection can be efficient. It doesn't really conform to these models.
Of a certain set of equations, right?
Right. Yes.
How many equations?
Well, we have fairly. Let me explain it when I actually show this. So we realizing that this is actually a simulation, but realizing that the system is large, nonlinear. There are no models that can successfully describe the evolution of the system once it consists of many interacting structures. On this slide, this is probably not a good slide to show now. So we are trying to approach this problem by ab initio simulations, and simulations are as simple as they can be for completely collisionless plasmas. Collisionless, yes, collisionless because in fact it is thought that collisional reconnection is slow, and actually those previous models they always had some collisional resistivity, and they were generally not very successful. Collisionless reconnection is thought to be fast, and those environments like jets and pulsar winds, they are also collisionless.
So you have the electron density, the ion density,
yes.
The electric field, and the magnetic field.
Well,
what else?
We have individual particles that are put on a grid. Those particles. So this is a completely kinetic model. The particles introduce density, charge density, momentum density, energy density, and so on. In the first step, now we have a grid of fields. The fields are the electric and magnetic fields. They govern. We make a simulation in the following algorithm. Once we know the fields, the electric and magnetic fields, we advance particles under the Lorentz force. Then we recalculate, once the particles shifted, we recalculate their charge and current density. We deposit the charge and current density at the right positions on the grid, and then we solve the Maxwell equations to advance the magnetic field, to advance the electric field. We also enforce satisfying the Gauss law and
That comes with Maxwell.
How large is the grid and how many particles?
yeah, so this is now just constrained by computers. I should say in the fluid simulations, we just have like matter would be represented by density, pressure, each one value per node, and so with
How many nodes?
with hundreds, we have of the order of hundreds particles per node. So this is approximately 100 times more expensive than fluid simulations. And now the problem scales up quite well. And so what I've been doing.
And this is of course in
was
3 dimensions, not in
I started from 2D. And
2D?
yes.
No, in 2D.
Okay, so
What
some
is
people
the
are doing.
justification? The
Yes.
magnetic field is completely
Yes.
different in 2 dimensions. Has no relation to magnetic field in 3 dimensions.
Yes, that's all quite true, but there are some good reasons for. Well, people did both 2D and 3D. They compared the results. They know how they differ. 2D is quite useful to begin with, and it's definitely more easy to handle. I plan to do some 3D later on, but let me
So also
show you.
particles and currents are confined to the 2D?
Yes, so, but the particles are have three-dimensional momentum. So
That's what I wanted.
Yeah, so this is called also 2.5D.
Yeah,
yeah.
I know.
So we use so the standard approach is to take this equilibrium. This is one-dimensional equilibrium.
Excuse me,
Yes.
does it happen in any external field or is it just field generated by the plasma itself?
It's the field that is put initially. We define the initial condition as predefined magnetic field. It is inverted on the certain length scale, and then there is a matching population of particles that supplies current density. The particles are we have XY plane, and the particle we have this Vx that depends only on y, and then we supply particles that propagate in the z direction. They supply current density, and they also supply pressure because they have some say temperature. We have collisionless plasma, but we put a Maxwellian distribution to those particles, which is only an initial condition. You can study acceleration. So this is an equilibrium, 1D equilibrium. When we put into the 2-dimension, it will break down due to so-called Terring mode instability. So let me now show an example how this works, and this is a little fast, but consider the initial condition is just one-dimensional, and then it proceeds already quite rapidly to produce plasmoids, and the plasmoids merge. Let me show it this way, and this is, as I said, only 2-dimensional. Now, initially this is showing the plasma density, this color, and it is now integrated along this layer. You see that already, I actually consider almost like one-dimensional problem because there is a symmetry due to the initial distribution of fields. Like there is a large domain of say positive field here, negative here. So most of the action is confined to this. Okay, we have fast generation of tearing, which makes these density structures, and they rapidly coalesce, and then there is this hierarchical growth of structures. So the plasma becomes dense locally, and it is so each of these dense regions is surrounded by its own. It basically forms a magnetic potential maximum. So then all these there's potential maxima, they try to merge. This is a periodic box. This is very simple and relatively cheap simulation, but so wanted to show the very rich phenomenology that is happening. Okay, so now what we can study by this, we have these density structures integrated along the plane. Then we have the average particle energy, and this is already very distinct from the density structure. So we have these dense cores, the plasmoids, surrounded by plasma that has been accelerated somehow, and it resides as a kind of low density halo around those high density cores. And then we can calculate where synchrotron radiation should be produced. This is astrophysically motivated, and the point of this is to evaluate radiative signatures that you may expect. And of course, the system is highly idealized, and lots of symmetries are being imposed. But what this experiment demonstrates is that you can expect highly localized radiation events. These are radiation events. Now, this is just the total synchrotron loss. These are synchrotron emissivities for individual observers, and we can convert it into light curves. So the events are being collected along the lines of equal observer time. For one observer or the second observer, you will see very sharp peaks of radiation. When we observe blazars or Crab nebula, we typically we evaluate the variability time scale, and using that we evaluate the size of the emitting region. What this reconnection model is the advantage of reconnection, I would say, is that reconnection can collect energy, magnetic energy, from a large box, and it will convert it locally in those magnetic X points, but they're just local points. Convert it into particle energy, and these are not necessarily actual emitting regions. The particles will emit when they actually meet with strong perpendicular field lines, but the emission regions are very compact. We can say that when we interpret some fast variability, we can consider in the reconnection scenario, we can consider that the energy that the magnetic energy that powers this emission comes from a much larger region. Fast variability means very tight constraints on the compactness of the source and lots of energetic problems. This already is one of the most useful insights from these experiments to actual observations.
What is really reconnection in this two-dimensional electrodynamics? Because the magnetic field has only one component, and the electric field has two components. So it's completely different from the three-dimensional picture.
No, I think it's a little bit misleading calling it 2D. This B, if you can stick out of the plane, isn't it? It's only assumed
Yes.
rather
Yes.
that the Z component is constant.
Yes. Yes.
So it's a three-dimensional
the
field.
thing is that
Three-dimensional field, or it's two-dimensional?
the grid is
No.
two-dimensional.
Electrodynamics.
The grid is two-dimensional, but the field,
The field components are three.
Yes.
there can be three components of the
Yes.
field.
So the field has three.
Yes.
Yes. Yes.
That's-
Yes.
So how do you handle Maxwell equations when you restrict this to
You just ignore the
uniform
Z
behavior.
dependence.
no dependence on Z?
Exactly, that's
Yes.
the.
Oh,
Yes.
That's what- This is what 2D means here.
Yes.
Okay.
Yes. Well, 3D. Yeah, as I said, people are doing 3D. Maybe.
No dependence on Z.
Maybe I will just search for.
Otherwise it
Okay,
would
I'll
make
go
no
back to
sense.
this slide. What other people did recently? These are recent statistics starting in 2014. People really started doing very large simulations of reconnection. So they have this very complex structure. We have like these large plasmoids, and there are even collisions of these large plasmoids. They generate secondary current layers. So this problem eventually would be almost like a fractal, if it would be a really a long system. But we know that the dimensional analysis tells us that astrophysical problems have this huge separation of scales, and simulations cannot really approach that. Well, what they show is that particles can be efficiently accelerated, and so there are these Powell distributions can be produced. The distribution index depends quite sensitively on the magnetization, and so these high relativistic plasmas can accelerate particles very efficiently, almost like the limit is the limit for infinite sigmas would be like p. So this is the number of particles per unit of per Lorentz factor is proportional to gamma to -1. So very efficient, actually, acceleration where most of the magnetic energy flows. A really substantial part of the dissipated energy goes to the highest energy particles. So the process is very fast. And this is a 3D example of 3D simulation, and there is this third dimension here, and it appears now that qualitatively the 2D results are comparable, just qualitatively comparable to the 3D results. And it was actually more controversial 10 years ago, where the simulations were smaller, and there appeared to be this additional instability of those. Now the plasmoids become magnetic flux ropes, and they thought to be prone to some additional instability that thermalized particles and did not allow efficient acceleration. Now it seems to be that there is no worry about that. Also, what's changed in the field recently is that relativistic shock waves that were being proposed for jets and for other phenomena, it turned out that they cannot accelerate particles efficiently unless the background is very weakly magnetized. This was bad news for AGN jets and for shock acceleration models. So now, reconnection is being actively studied, and there is a lot that that I'm trying to do. Now, I don't know how much time I have. Okay.
This clock is late.
Yeah, so it's late, so
Okay. So,
Yeah, it's 11.
it's 11.
so yes, so I've been trying to measure the signatures of synchrotron radiation from these simulations. I should also mention, in relation to this problem of the crab flares, synchrotron radiation can indeed exceed the classical limit when particles are accelerated in E greater than B, and this has been confirmed by these types of simulations. What we are been doing more recently, and this is yet another classical model of reconnection, but slightly, well, so the model involves the merging of two magnetic domains, and they have one neutral point between them, and this is an analytical solution from the 60s. This is really beautiful, and I should say, very brave effort. I cannot say, well, I can say it shows you the main features of what would happen. However, these hatched regions are where the MHD approximation breaks down, and he knew that it breaks down here, and he could not give you a full solution. And this hasn't been advanced since then. Recently, actually, there are two groups that independently pick up this model, and we made a setup, very simple setup, just harmonic fields, fields that satisfy the so-called Bertramian condition. So, and again, we can do it also in 2D if we ignore the Z dependence. And I'm basically set up this the periodic box here. So when this is magnetic field. The color is magnetic field, the Z component, but also the magnetic potential component. So this is a nice problem in which the two maxima and two minima of the potential they attract each other, and when the symmetry can be broken because they are interlocked, they will reconnect part of their energy. And let me skip the movie and just show you how this works in the simulation. So we have the BZ map, density map, and the average particle density. So initially, well, this is not exactly the initial condition, but there's just the beginning of interaction. So by a little shift in the positions of these domains, these two start interacting, and they form a current layer between them, and the other two also form current layers.
So are these solutions of Maxwell equations?
Yes. Yes. So we, well, yeah.
But Maxwell equations are linear, so it should be quite easy to calculate this.
Well, but there are some slides. There's chaos in the particles, and
so these are Maxwell equations coupled with
particles. Yes, yes. I mentioned that there is like 100 of the order of 100 particles per. Yeah. Each particle is responding only to the fields, and for example, the breaking of this symmetry could go either this way or another way. This is decided only by the noise in the initial particle distributions.
But this is all in this idea of particle in the cell type simulation.
Yes, yes. But this is.
So when you are saying you got hundreds of particles per cell, it means that that's represented by only one particle actually.
No, so I should say that each particle has a large mass. Like it would be a collection of
yes, representing collection.
Yes, but
exactly.
Due to just numerical capabilities, but why peak is well, people were trying to do. Of course, when you do magnetohydrodynamics, there is a large business of doing magnetohydrodynamics. Idea of magnetohydrodynamics breaks down eventually in those current layers. The current layers, I didn't show the current density, but it would be, the current layers are here, and the heat particles. You can see that the regions where there is high particle energy are aligned with those current layers. No, well, people can do a two-fluid MHD to have separate fluid for, and this is per plasma also. This is the simplest case. Having electron-proton plasma introduces the mass ratio that requires even larger resolutions. So for simplicity, this is per plasma. But fluid simulations, they usually break down at some point, so they cannot describe well this physics of current layers, the acceleration of particles, and from peak we have both these maps, but also the particle distributions. So we can actually measure particle distribution as a function of time. We have initially this relativistic Maxwellian evolving very rapidly actually towards power law distribution, and we can measure these power laws as for different simulations. So this is quite powerful tool, and we made it even more interesting when we introduce radiation package. We introduce, in addition to pushing the particles by Lorentz force, we also introduce radiation reaction due to synchrotron radiation and also inverse Compton. And this is work in progress. The radiation signatures are like the key element of this, because the only way to verify these models is by comparing them to the observed radiation, to observe gamma rays from space, because reconnection in relativistic regime, as far as I know, it cannot be studied experimentally, and it is already quite different from the closed space environment. So we only have radiation to tell whether we are right or wrong. And if I'm out of time, then I can stop here.
Yes.
So the particles you're using are fully relativistic.
Yes. But it can be done also with non-relativistic particles. Here we initiate with Maxwellian with this KT equal MC squared. Just we can choose different temperatures.
In terms of computer power, if you would just take n particles and couple them through any sort of Lassov equations with electromagnetic field, how many particles can you handle with reasonable computer power?
Yeah, so these simulations already involve at least 1 billion of particles.
But of course you do not follow each of them separately.
I don't save. It's more like data management problem, that storing the result of all particles in every time step is prohibitive due to time it takes to write on the disk or disk space.
But my question is, how many particles could you handle in
Of
this
the order of
If-
billions.
billion,
Yes.
following
more.
each particle.
No, he's not following
But
it. He's
No.
replacing
Yes, but my
bunches
question,
of
but
them
the
by
processor-
yes, I know, but my
Yeah.
question was, if you take n particles and follow each particle separately,
Yes.
how many particles can you handle in this way?
I'm not sure if I understand the question because
You
the
couple-
processors, they compute every particle propagation separately.
Sure,
But there are like hundreds of or thousands of processors working together on each on their own set of particles.
yes, but if you would just follow each particle and store the position of each particle
Yes.
and the
and
velocity,
velocity.
what is the upper limit with reasonable computer
Yeah,
power?
well,
Without this approximation, without
This so-called peak.
okay.
Yeah.
So what I can say that it depends more. Probably it depends more on the disk space that we have. So I would say maybe hundreds of thousands to a million of particles. Like,
Ah, so then,
so
In
would-
3D?
in 3, yes.
Well, not in, well, that would be really very low resolution because the particles. Okay, what I do here is that I from this billion of particles I save maybe 100,000 for detailed analysis.
Yes.
But
But
it's for very small simulations one can save all particles, but eventually there is no point.
But has anyone done this with all the details of particle dynamics in 3D? Because that
yeah.
would give some idea what is
Yeah, I
the
should.
mechanism.
The-
Can one
another,
get these
another,
reconnections in
another
this?
practical problem is how to describe what each individual particle is doing. It's a very complex, chaotic
No, it's,
picture.
why do you call it chaotic? I mean,
Yeah,
these are differential equations with the Lorentz force
yeah, but like,
and Maxwell equations coupled to this.
yeah. I should also say that
And there should be some signature here of this relativistic.
Czy jakieś statyczne oddziaływanie
No, there is no. Okay, so what people do? Actually, people do more advanced simulations for space plasmas where they take into account the collisions of particles. Collisional peak is possible to do, but then it cannot be done.
No, I
as
understand
accurately.
collisions are a different matter, but
Yeah.
I'm thinking about
Yeah.
collisionless situation.
Well, I can also track histories of individual particles, so like those selected ones. I can see how they gain energy, where they go, but eventually it's part of the difficulty here is to make a full analysis of the results because there are so many results that can be produced, and 3D is even more difficult.
Final question. So you mentioned these export points or small regions in space where the reconnection happens. Is it possible that the reconnection happens not in localized points, but rather on some higher dimensional structures like filaments? Or does it have to happen in localized one-dimensional structures?
Well, I think these models that were initially proposed, they had these extended structures, but due to these constraints from mass conservation, the process appeared to be rather slow. So now the benefit of having these localized magnetic dissipation regions is that the process can operate more efficiently. So just localized, but at higher rate. And there is still discussion on whether this process can work even more volumetrically. Like if there would be like probably for the crowd, it would be really nice to identify possibility to create volumetrically extended electric fields. So that may probably involve if there are really a small number of charges, there is a charge start situation. So then there are some global potential gaps open, and this kind of models have been discussed in the Palzer literature. Then possibly yes, but I'm not sure if that would be still called reconnection or some different type of.
No dobrze, to już chyba
To co, to może